Okay, hello everyone. My name is Lucas Shi, and I'm here today to answer the question, how does the theory of inflation have implications on the quantization of gravity? Now be sure to read my paper when it comes out. Now, an overview on the topics we are going to talk about today. First, we're going to talk about the inflationary theory and the genesis and beginnings of the universe. Secondly, we're going to talk about experimental evidence of the inflationary theory via the cosmic microwave background. We're going to tie these concepts to the fundamental forces of the universe and how inflation can reconcile these fundamental problems in physics. And lastly, we're going to tie everything in a little string, or more specifically, string theory, and how it can provide a unified framework for the universe, and how by utilizing experimental evidence, we can prove or disprove this theory. Now, let's move on to the inflationary theory. Inflationary theory is in a subfield known as CMB cosmology, which concerns the very initial conditions of the universe. This allows us to quantize gravity and is the only experimental field that allows us to do so. The inflationary theory is an exponential expansion of the universe that expanded the universe 10 to the 26 times its size in less than a fraction of a second. And due to this volatile event, it caused repercussions through space-time known as gravitational waves. And through these gravitational waves, scientists can utilize it to derive important information about our universe. Now, let's talk about the three main problems plaguing the Big Bang model, which is the model of the universe that has a genesis to it. Now, in the 1970s, before the advent of inflation, there was three main problems. The first one was the horizon problem. How could different parts of our universe have interacted if the universe was expanding beyond the speed of light? We have detected photons from 48 billion light years away, yet our universe is only 13.8 billion years old. Yet from experiments, we have found that our universe is relatively even in density, meaning that different sections of the universe have had to interact with each other. However, nothing travels faster than the speed of light. And therefore, how did the universe become so even and stable in density, despite not having different parts interacting? Secondly, we have the flatness problem. Why does our universe appear to be so flat? Now, I know that flatness in a universe is a rather abstract concept. So if you have any questions about it, please feel free to ask about it in the Q&A session. Now, the magnetic monopole problem. Again, a magnetic monopole is a type of fundamental particle predicted in the Big Bang model. However, scientists have failed to detect a single one of these particles despite the model stating that these particles should be pervasive. So why have we not found these particles in nature? Now, let's talk about how the inflationary theory kills three birds with one stone. In addressing the flatness problem, imagine if scientists were ants and scientists were on a balloon. Now, if I had superhuman lungs and I could blow this balloon up to enormous dimensions, then from the ant's perspective, the curvature of the balloon would appear to be more and more flat, analogous to our perspective of the universe and how it appears to be flat, because inflation has dilated the curvature to such an extent that it becomes negligible. In addressing the horizon problem, imagine if I had a ketchup stain on the balloon. If I stretched this balloon to enormous dimensions, then the ketchup stain would become almost unnoticeable. And finally, analogous to the horizon problem given in the Big Bang model. And finally, addressing the magnetic monopole problem. If particles, which basically states that if particles were formed, the no-hair theorem states that if particles were formed before the period of inflation, then they cannot be observed in nature because they have been dilated so much by the inflationary event. Imagine if I had a bag of marbles and I had the marbles spread out inside the balloon. If I expanded the balloon to such an extent, it would be extremely hard for me to find one of those marbles again. Analogous to that, magnetic monopoles were formed before the period of inflation, which is why they are not observed in nature today. So that is a check, and a check. Now, you might be asking, Lucas, okay, so the theory of inflation solves these three main problems in Big Bang cosmology, but can I actually make a detection of inflation to prove the inflationary theory? Maybe. We know that there is a way to find a direct measurement of inflation if inflation exists. However, we have not found the signal yet, but we have indirect evidence of inflation via the cosmic microwave background and of the three problems of cosmology. Now let's talk about the cosmic microwave background. Essentially, the cosmic microwave background represents the first light of the genesis of the universe, or at least the first 400,000 years of it. And therefore, because inflation was in the first 400,000 years, we'd be able to detect it as a measurement in the cosmic microwave background. For you guys to get a more tangible sense of what the cosmic microwave background is, here is a picture of it, in fact, in the electromagnetic spectrum in the microwave region. Now, as you can see, there are some blue spots and there are some red spots, and these correspond to the different polarization patterns, or in simpler terms, the different orientations of these photons. And fun fact, these photons, the orientation of these photons and this pattern correspond to quantum fluctuations in the genesis of the universe before inflation happened. And if they had inflated to their current positions, this is what they would have looked like, providing indirect evidence for the inflationary event. Now, you might be asking, Lucas, how the heck can light particles absorb information? Well, the CMB is a black body, which in physics means that it's as good of an absorber as it is of an emitter. And by analyzing their signal of absorption, we can extract a lot of important information. And by detecting a direct signal of inflation, we'll determine the quantization of gravity. Now, why is quantization of gravity such an important concept? Because physics right now has to use two contradictory frameworks to describe phenomenon. Quantum mechanics for objects at the minute level, and general relativity for things at galactical scales. And physics right now cannot reconcile that discrepancy. So putting both of the frameworks under the same umbrella would be a significant achievement in the field of physics. And the inflationary field and the inflationary theory would seek to reconcile this difference, which I will get to in the next slide. Now, let's talk about how the inflationary signal will help find a unified theory or quantizing gravity. Because the inflationary signal was from a time when the fundamental forces hadn't split apart, as you can see from the diagram here. When the energy of the universe was at such a high level that the four forces weren't different threads like this. They were all from the same thread. And therefore, if we were to detect an inflationary signal, we would be able to use it to derive important information about what physics would look like if the forces were unified. And that ties back to the question of string theory, because string theory, the main appealing point of it is that they offer a theory of everything, a theory that can unite the four fundamental forces and unite the quantum and the gravity forces under the framework of a cosmic string, how all particles are composed of different vibrations of said strings. And by probing the CMB, one day when we may actually discover the inflationary signal, we may use the information discovered about the inflationary signal and the four forces held together to prove whether string theory and its theory of everything should be used in the future, and whether it should be proved or disproved. So in summary, the inflationary signal is important in finding the large scale structure of the universe, in reconciling the difference between the quantum and the gravitational forces under a single framework, and proving or disproving string theory. Here are my works cited, and feel free to ask Q&A questions. Thank you.
Awesome. Great job, Lucas.
Thank you.
So again, for all the audience members, feel free to drop any questions in the Q&A section at the bottom of your screen. I actually did have two questions that I wrote down, Lucas. One is kind of a general question. The James Webb Telescope, has that had any impact on the research that you did, and the theories that you're discussing here today?
I believe that the James Webb Telescope, I think that they have had some they took pictures of far away galactical systems. I haven't done any research into that field yet, but as of what I've heard, the James Webb Space Telescope has improved our understanding of many cosmological fields dramatically. But in terms of the CMB, I think that one of the more significant achievements in the few years was the Planck telescope by the EU, and how it provided a more detailed and pixelated image of the CMB picture, as I was showing.
Great. And actually, just to dig deeper on that, what are the differences between the James Webb Telescope and the one that the EU is using? I'm not sure. I didn't catch the name of that telescope.
Oh, the
Just
Planck
the
telescope.
differences. Yeah.
I believe that the James Webb Space Telescope is I think it has a multitude of sensors. It doesn't just have the one used to detect the CMB. It has different infrared pictures of galaxies from millions of light years away. I think it's higher resolution than the Hubble Space Telescope, and I think it's still processing the information back to Earth. But I remember reading an article talking about how the James Webb Space Telescope could potentially find that inflationary signal that I was talking about in the presentation.
Great.
And the Planck.
Okay. Oh no, sure, go ahead. No,
Okay.
that's okay.
And the Planck telescope, I think it only has sensors for directly toward the CMB and all that. So I think there's a little bit of discrepancy in the function in what they do. Yeah.
Great. No, I appreciate that comparison there. So Tyler has a great question here. How close do you think we are to a more unified theory, and are we limited by technology right now?
My mentor talked about finding the inflationary signal, in the CMB signals. And I was asking, isn't it supposed to be easy? You just find the CMB particle and you just pick it apart. And then she was like, it's not that easy because, again, the inflationary signal was from the very, very first signal ever come out in the universe. And there's a lot of junk associated with finding the inflationary signal because there's a lot of different things that the CMB photon went through. For example, if you're trying to find a gravitational wave, as you can see on this diagram, I'm not going to go into the specifics, but it talks about lens B modes, and that's how B modes go into black holes, come out, and their signals completely changed. So it's really difficult to find that signal. And I was reading an article, it talked about how our telescopes and our detectors, it's getting more sensitive, so it can detect B modes at a lower and lower scale. And I believe I was reading the article, it talked about a new generation of these detectors and how we are getting sort of close to the level in which we can perhaps find the inflationary signal, but I think we're still 2 degrees of magnitude off. Yeah.
Great. And we have one more question here from an anonymous attendee. Are you planning on continuing your research? And if so, what would be your next steps?
You know, I came into the Polygence program trying to find a more of an explanation on string theory and like the nuances and things about that because I feel like string theory is a really important thing in physics that we should look out for right now. Like I read a lot of articles on it, I read a lot of like books on it, and I believe that it's like a really cool concept, right? Like everything out there can be described using the vibration of strings. Now, like my mentor kind of like diverted my track a little bit to like focus on like, going from the experimental evidence to something more theoretical like string theory. But I feel like if I were to continue with Polygence and to make another project, then I would focus more on the theoretical aspects on like string theory and all that. And I remember one more limitation that I had when I was starting this project because like I was in 8th grade at the time and my math knowledge wasn't like sufficient enough to keep up with this like, advanced math, advanced physics, advanced calculus. Like my math is getting better. So perhaps if I were to like continue with Polygence next year and having some maybe like basic fundamentals of calculus, I could advance my like knowledge to the next level. Yeah.
Great. Well done, Lucas. Definitely appreciate
Thank you.
the hard work that you did for this project, and really, really well done.
Thank you.